Some of the most familiar and widely used effects in recording and mixing are based on the acoustic phenomena of direct and reflected sounds in combination, and the related psychoacoustic perceptions of our hearing systems. The phase interference and comb filtering effects of direct and delayed waves, and the Haas effect that governs how we perceive the sound in those situations, is the basis for the classic effects of flanging, chorusing, doubling, and echo. And the combination of dense multiple reflections, when simulated with digital delays, gives us our artificial reverb and ambience processors. Without these various effects, most of our multi-tracked recordings would be painfully dry and flat. In this course, I'll go over the basic operation of these effects, including all the relevant parameters, and some of the classic applications. But first, I'm going to do a brief recap of the relevant acoustics concepts these effects are based on, which I covered in detail in the previous course in this series. When we're hearing sound in an enclosed space, we're hearing not only the direct sound waves from the source to our ears, but also many reflections of those waves from the room boundaries, walls, floor, and ceiling, and other surfaces in the room. These reflections combine with the original waves and with each other, causing phase interference. When a wave meets up with a reflected, delayed version of itself, the interference that occurs is based on the relative timing of the cycles of the two waves. The duration of a cycle of a sound wave is measured in degrees of phase from 0 degrees through 90 degrees, 180 degrees, up to 360 degrees. If a delayed reflection is at 0 degrees relative to the original direct wave, you'll get reinforcement of the sound. If the delay is at 180 degrees, you get complete cancellation. In between, you get partial reinforcement or cancellation. Since the specific result is based on phase, which is a function of time and frequency, when this happens with complex waves, the different harmonics and overtones that give the wave its tone are affected differently. Some are reinforced, others cancelled, and as a result, the balance of harmonics and overtones is altered, and the tone is changed. This is called comb filtering, which is the basis for most of the effects I mentioned before. When direct and reflected waves combine like this, the way we perceive the combination depends on the amount of delay involved. A rule of psychoacoustics, called the Haas effect, describes our perceptions. If the delayed sound arrives less than 30 to 50 milliseconds or so after the direct sound, then our brains fuse the two together, hearing them as one sound, with its tone altered by the comb filtering effects of phase interference, which I just described. This shorter delay range is called a fusion zone. If the delayed sound arrives later than 30 to 50 milliseconds after the direct sound, we hear the two waves separately, with the delayed sound perceived as an echo, the echo zone. The Haas effect is also known as the precedence effect. When direct and delayed waves combine within the fusion zone, and the reflection comes from a different direction than the original direct wave, not only does our brain fuse them together, but the combined direct and delayed sounds appear to originate from the location of the original direct wave. Our hearing systems localize the resulting fused sound to the location of the first arriving wave. This is known as the law of the first wavefront. Again, these acoustic phenomena and psychoacoustic perceptions are the basis for the effects that are the subject of this course. If you feel you need a clearer understanding of them, and haven't gone through the acoustics course in this series, you could back up and get some more detailed explanations of all this, or just refer back to that course as a reference whenever you feel you need a little clarification. Next up, I'll get started by looking at the delay times for the various delay-based effects.